All right, good afternoon and welcome back to Analog Electronic Systems. So, in the last class, we looked at examples of first order low pass and high pass filters and saw how we could realize them using passive elements that you are very familiar with. And we also saw how you can realize them with op amps. The advantage with an op amp being that the the transfer function does not change with loading, and the transfer function is also insensitive to stray capacitances that can occur at any at any node. And finally, you can also it also gives you the freedom to be able to increase the DC gain or the pass band gain of the filter to beyond 1. In the passive prototype, they were all constrained to be 1, but in the active realization, you can actually increase that to something greater than 1. The only drawback, if you want to call it a drawback, is that the transfer function had a negative sign. The DC gain was negative, right? And that can be easily fixed by putting another inverting stage with a positive DC gain. With another negative DC gain, it can either precede the filter section or after the filter section, and that's basically what. Okay, now let's move on to second order filters. So the transfer function. So So this is what is called the standard form of the second order low pass filter transfer function. The DC gain, what is the DC gain? The DC gain is obtained by simply putting S equal to 0, that's equal to 1. Now, the magnitude of, so where are the poles located? To find the location of the poles, what do we do? Well, we just simply find the roots of the characteristic equation. This is now a second order equation. So, S upon omega p q p plus 1 equal to 0, all right, and therefore, the poles are at minus b, that is minus 1 over minus b plus minus square root of b square minus 4 omega p square divided by what? 2 over omega p square. All right. So, this is now minus omega p over 2 q p plus minus square root of okay. All right, minus 1. Okay, then what happens? What about the first term? Yes. What is the first term? Yeah, please work it out and tell me. Omega p square over 4qp square minus omega p square. All right, which so that can be written as minus omega p over 2qp plus minus omega p times square root of 1 by 4 qp square minus 1. Is that clear? Okay, three cases arise now. Case 1 is when 1 by 4 qp square minus 1 is greater than 0, it's positive, all right, which is equivalent to saying 1 by 4 qp square minus 1 greater than 0 is equivalent to saying qp is less than 1 by 2. So, for qp less than half, the what comment can we make about the roots? The discriminant is positive, so the square root is basically real. So, two real poles, and where are the two real poles? They are on the, I mean, if they are on the left half plane is understood, because if q is positive and omega p is obviously positive, then all the coefficients of the equation are all have the same sign. So, the poles must be on the left side, left half plane. But where in the left half plane? You have two poles on the negative real axis, and the poles are at minus omega p times 1 over 2 q p plus minus square root of 1 over, actually you can remove the 1 over 2 q p also outside, I believe. One plus minus square root of 1 minus sorry 1 minus 4 qp square. I hope this is right. So, multiply throughout by 4 qp square 2 qp. I think this is fine. Okay. All right. By the way, this omega p is called the center frequency or the natural frequency. QP is called the quality factor. All right. So, the quality factor is less than half. Then you have two real poles. The two poles are on the negative real axis, okay, and at these locations. Make sense? Case 2, 1 over 4 qp square minus 1 equals 0. Then this corresponds to qp is exactly half. Then what are they? Where are the poles located at? How many poles do we have? You have a second order denominator. How many roots will be there? How many poles do we have? Okay, and where are the poles located at? Yes, minus. How did you get omega p? So from the quadrant, so where are the two poles? By so we have a case of I mean, if QP is exactly half, then the polynomial becomes s square by omega p square plus 2s by omega p plus 1, and this is basically as you can see, this is a perfect square. So this is nothing but s over omega p plus 1 the whole square. So the pole is at minus omega p, right? You'll have two poles at minus omega p. So you still have two poles, two roots on the negative real axis, except that these two roots are coincident at omega. Okay. All right. Now, so real poles at minus omega. Now, case 3. Is when 1 by 4 QP square minus 1 is less than 0, correct, which means that QP is greater than half. And now what happens? Well, the discriminant is negative, and therefore the square root of that will be imaginary. So this is the poles are at so basically minus omega p over 2 QP plus minus omega p times plus minus j omega p times square root of 1 minus 1 over 4 QP square. All right. So you have, this is the S plane, right, and so this is you have two complex conjugate poles. This distance is omega p over 2 QP. Very good. And what is the magnitude of these poles? Just please sit and calculate if you are not able to look at it and tell me. Omega, very good, right. So basically this distance is actually omega p, independent of q, correct. So so as q goes on increasing, what comment can you make about the locus of these poles? What is the meaning of locus? If I keep changing q, for each q I will keep getting location of two poles, right. If I join all those points, what will I get? What did we say just now? What comment can you make about the length of that of the distance of the poles to the origin? It is omega p and it's a constant. So as you keep changing q, what comment can we make about the locus of those roots? It is a circle, right? So, this is j omega p, this is minus j omega. Is that clear? That makes sense, people? Okay. Now, this is what happens with with uh, uh, with q, and so this corresponds to this point corresponds to q equal to half. If you have q just a little bit greater than half, the two poles will be there. As q keeps increasing, the poles will move along the circle, and for q equal to as q becomes higher and higher, the poles become q becomes higher and higher. Where do the poles go? So, this is the locus for higher. As q keeps increasing, the poles move along the circle towards the j omega axis. For q equal to infinity, where are the two poles? They are on the j omega axis. Is that clear? Okay. So, so basically, for q, obviously, being negative, then the poles are in the right half plane, and they are not useful because the system is unstable. Now, what is the so to summarize our discussion so far, with a standard second order denominator, namely second order filter, low pass filter, this is 1 plus s by omega p q p plus s square by omega p square. We have three cases, q being less than half, where you have two real poles on the negative real axis, q being exactly equal to half, where you have two poles, repeated poles at omega p, and q p greater than half, where the poles are complex conjugate, and as q p keeps increasing, these poles move closer and closer to the imaginary axis.